Dear embedded systems learners, in this session we will learn about the interrupt programming with AVR microcontrollers. So let us start the interrupt programming in AVR microcontrollers. So here is the Atmega32, which is one of the AVR microcontrollers. Its pin diagram is there. It is 40 pin microcontroller. We can see the pin numbers. There are main four ports, port B with 8 pins, port D 8 pins, port C 8 pins, and port A is also of 8 pins. So there are 4 I/O ports, each of 8 pins. So here important to note is that as we are discussing interrupt in this uh, session, so interrupts are these pins specifically. Here it is interrupt 0, which is at pin number 16, which is PD2, port D, pin 2. Interrupt 1 is pin number 17, and there is one more interrupt for this microcontroller. So, because each microcontroller may have different number of interrupts, so the interrupts may vary according to different family of microcontrollers. So the third interrupt for this microcontroller is this one, interrupt 2. So these three external interrupts can be used, whereas the timer interrupts are related to timers, which are also three timers in this microcontrollers. However, we can use more than one interrupts related to each timer. So we will discuss the overall interrupts in next slides. So first, before going into detail, here is bit text related to interrupt versus polling. So idea is very logical, interrupt programming and polling. Polling is actually the scheme of handling the code when the microcontroller executes all the instructions in sequence wise, step by step. Maybe there is no any requirement for the any particular device or pin, but all the instructions will be executed in the sequence. So there may be wastage of time in case of polling because of having checking all the pins. But interrupts programming, it is more efficient in that our device or microcontroller can do one task at the time, and another task or more than one task can be entertained if there is an interrupt from those tasks. So irrespective of the other tasks, it can concentrate on only one or two tasks, and interrupts are efficient while managing more than one task. In this way, we can say that interrupt programming is better approach than polling in most of the cases. So there is an interrupt service routine. Routine is actually function in microcontrollers programming. So it is actually the part of codes which are specific to an interrupt. So whenever an interrupt occurs, there is a routine or function associated with that interrupt. So that part of the code is called interrupt service routine. Next, there are actually the steps in executing an interrupt. So these are again very logical, as whenever we do any task and there is some interruption, so we do according to the importance of that emergency interruption, or we may hold on that interruption. So as per the condition, the first of all, like we do, microcontroller does that it finishes the current instruction which is being executed while an interrupt occurs. So it executes that instruction and saves the address of next instruction. Very next instruction address is saved on program counter so that it can be tracked when coming back towards the normal function. So step 2 is It jumps to interrupt vector table. Interrupt vector table contains the information about all the interrupt service routines. So information about where that ISR will be residing in the memory. So controller goes towards interrupt vector table. From there, it takes the information about particular ISR location. And in the third step, microcontroller starts executing interrupt service routine until it reaches the last instruction, which is return interrupt instruction. So after this, it goes back to it wants to go back from where it was interrupted to go back that place. It takes the information from program counter, which was the register responsible for uh, storing the next instruction location or address. So it again restarts its normal activity and it keeps on performing that routine until any other interrupt occurs and so on. So this is interrupt vector table which was mentioned there in step 2 out of 4 steps. So each interrupt, here we can say that there are a number of interrupts. Reset is the most popular one which we use daily in our daily routines while dealing with mobile devices or computers, that when our system is reset, the ROM location to where the device or computer or controller should go, that is location 000. So same is the logic. Like whenever external interrupt 0 occurs, the device should go to location 0002 ROM location, and for interrupt 1 at 4 location, and for interrupt 2 at 6 location. Similarly, there are timer interrupts like timer counter 0 interrupts are here, 2 interrupts for timer 0, these 4 for timer 1, and these 2 for timer 2. And there are also the interrupts related to communication and analog to digital conversion and other processes related to the storage devices. So mainly we discuss uh, external interrupts in this session, which are actually 3 in number. And while programming the interrupts, we should be careful about the location of these interrupts. That interrupt 0 should be handled at location 2 and so on. So what are the sources of interrupts in the AVR? This is actually the summary of the last detailed table. And there are interrupts, external interrupts like interrupt 0, 1, and 2 at these specific pins. There are serial communication interrupts, there are SPI interrupts, there are ADC interrupts, in addition to the timer interrupt. So all these are the interrupts which can be programmed while using this AVR microcontroller. So here it is actually the structure of the AVR code while dealing with interrupts. So whenever we program the interrupt coding, first of all we fix the location. Here it is origin 0. So main function is placed at location 0 and other details can be placed at anywhere else. So here after setting location 100, the details of main function has been put forward here because there is limited memory, as we discussed here, that only 2 bytes are for reset, only 2 for interrupt 0 and 2 for 1 and 2. So that is why the detailed part has to be written next, maybe after 100 location or so on. So that is the major structure of writing interrupt programming. So one concept related to interrupt programming is about enabling and disabling an interrupt. So all the interrupts by default are not enabled, and it should not be enabled by default, because in that way it can be a mistake in programming that if we don't need an interrupt, but in background it will be interruptions. So start all interrupts are disabled, which is also termed as masked interrupts. So unmasking is actually the process of enabling the interrupts. So at two levels, interrupts are enabled. The main level is the global level interrupt enable that is done at bit 7 of status register. So even if locally an interrupt is enabled, but if this bit is disabled, then all the interrupts will be treated as disabled. So this is global level enabling and disabling, and there are also at lower level uh, interrupts enabling and disabling. So with single instruction, which is clear interrupt, we can make this interrupt bit 0, this D7, and by doing this, the interrupts will be disabled. And and the same process is used for enabling the all interrupts at global level if we make it 1. So we set this bit 1 for enabling all the instructions, all the interrupts. Here it was the mentioned D7 bit of status register, which is the global interrupt enable. So this should be 1 for enabling all the interrupts at global level. And if it is 0, then all the instructions would be disabled. So in summary, what are the steps in enabling interrupt? To enable any interrupt, we take two steps. Bit 7 of this register is set high, and to do so, we use this instruction, which is set interrupt. As CLI is clear instruction to disable interrupts, but to enable interrupts, we use SEI. And at second level, if we have done this, I is equal to 1 by following step 1, then related to all interrupts, there are individual bits like timer interrupts are enabled and disabled at this register TIMSK, and other registers are used. So relevant bits are made high or low to enable or disable the corresponding interrupts. Like here is detail of TIMSK register. This register is responsible for enabling and disabling all the timer interrupts locally or at second level. Like for example, this bit D0 is related to TOIE0, which is this one. So if this is 0, if we program it 0, then it is disabled, timer 0 overflow interrupt. We know that it is overflow concept of timer while programming or configuring timer. And if it is set 1, then this interrupt is enabled. So likewise, all the timer related interrupts are enabled or disabled by setting the corresponding bit to 0 or 1. So here in this example, there are some practices for enabling and disabling interrupts. Like in A, it was required that to enable the timer 0 interrupt, overflow interrupt, and timer 2 compare match interrupt. So accordingly, that bits which were mentioned in previous slide about a TMSK register, those bits are made high once. So after doing this, these values are loaded into TIMSK register, and this is global level interrupt SEI and the bit 7 of status register. Similarly, in task B, we want to disable the timer 0 overflow interrupt. To do so, we uh, set the configurations in this way, or it is also possible to do in this way. So there are multiple options. So these are actually being done in assembly language programming, and in task C, it was to disable all the interrupts, and to disable all interrupts, we just have to use this command, which is CLI clear interrupt. In this way, global level interruptions are disabled and all the instructions are now disabled. So next we will discuss the practical interrupt programming. Uh, Programming external hardware interrupts is the main topic in this session, as there are different types of interrupts like timer interrupts. These are external hardware interrupts, and other communication and analog to digital conversion interrupts, but now we will focus only at the external hardware interrupts. So there are three hardware interrupts. So we can use three different external hardware interrupts according to our requirement. So the logic is that whenever an interrupt occurs, that interrupt service routine is executed, and then the system comes back to the normal routine. So here is our register. The logic of overall programming of AVR controllers and almost all of the controllers is that there are some specific function registers which are to be configured. Like this is general interrupt control register. There are 8 bits. Usually there are 8 bits in all this AVR microcontroller. So interrupt 0, interrupt 1 and interrupt 2. Three interrupts can be either disabled or enabled according to their relevant bits setting or resetting. So this is interrupt 0 related bit. If we clear it in coding, then this interrupt will be disabled. So it will not be working. So to use this interrupt, we will have to set this to 1. And similarly, other interrupts can be configured. So we configure this type of settings in our coding. So here is first application written in assembly language. So idea is that we are to use interrupt 0 out of interrupt 3 interrupts. Interrupt 0 is to be used, and interrupt 0 is actually at pin D2, support D pin 2. So interrupt is such that we are to write a program that toggles port C.3. That means pin 3 of port C, which is this one, that should be toggled, and we know that toggling is just switching from one to low, high to low, and low to high, and so on. So this is toggling, also called blinking. So whenever this interrupt at this pin, which is interrupt 0, occurs, how it occurs, because it is stated that normally this is high. So internally it is set as high. Whenever someone press this switch to low, as it will be pressed, the ground will be over here, so it will become low pin. So low interrupt enabled is this one. Then the program should do the port C3 as toggle. Mean if it is earlier at high position, then it should change it to low, and if it was at low position, it should change it to high. So this is the objective. Otherwise there is no any other task for this program. So that is why normally when overall in this code, if we see that here this command which is labeled with here, and this is the line where the controller is idle, it does nothing, and it stays here. Whenever this interrupt occurs, that it is pressed to low, then it serves the interrupt. So as we discussed that every interrupt has special allocation. Like here, origin 0 is used for main function, and then main function is programmed or written over here after this interrupt related uh, indication, as interrupt 0 is located at location 2. So that is why it is very important to mention this origin 0 2, and then we can switch or jump our ISR interrupt service routine, which is related to our external 0 interrupt, to somewhere else. So here we are jumping this code to this one. So after once interrupt occurs, the controller goes to relevant location 2, and then we send it or divert it to location this one, which is labeled as this EX0 ISR. So this is external 0 ISR. We may set any of the name or label. It depends on the actual background of the purpose. So here ISR, we will be doing that function which is required. The requirement is that just toggling of the bit. So before discussing this ISR, we should go through this part, which is main function. In main function, these lines are related to uh, setting the RAM stack pointers, and after that, which are usually we do as we discussed in previous sessions, and after that we initialize the stack. So this is also related to stack. So this is overall stack setting lines, 4 lines. After that we make port C pin 3 as output, because here we are to set it as output. So SBI in assembly language does set bit instruction, so it makes the bit equal to 1. So whatever is bit number of this register, it is made 1. So port C related register is DDRC, which is configured to high or low for output and or input. As this is to make output, so we set it. And port D is actually input, so we make it as the interrupt setting parameter. So here we actually activate it internally. So that is why we used it as SBI. So we set it as 1, because on occurrence of interrupt it will be low. So normally it is high, it is pull up activated, and these are the steps which are related to enabling interrupts. Here we enable interrupt 0 bit of this interrupt is loaded into this GICR register which we discussed in previous slide, and that interrupt is enabled. And after that SEI set interrupt enable, which is global level enabling of bit 7 of status register. So in this way we have done enabling at both levels, global level and as well as local level. So now our interrupt is ready to be served. After that our controller stays here, it jumps here and here. So here is again the same line, so it does nothing. So whenever this switch is pressed, from here it goes to location 2, and from that it is diverted to this label, and here it is toggling code. And to toggle code we are required that first we should read what is status previously, whether it is high or low. If it is high we are to make it low, and if it is low we are to make it high. So that is why we use pin C register to read this status of this pin, and we read it in R21 general purpose register, and then we load a value 8 into another general purpose R22 register. And if we look over here, this is bit 3 related to this toggling. So this is 08 in hexadecimal, in this binary this is 08. So we load it in R22, then we take exclusive R of this, and whatever is the status practically or physically over here, whether it is high or low, we take its exclusive R, and answer or output is stored in R21. And after that we send whatever it is, because after taking exclusive R, the bit is toggled. If it was high it will become low, and if it was low it will become high. So after this exclusive R we just send this value R21 to port C at the output, so the output would be toggled. And then return interrupt instruction sent back to the base where it was doing any task, but it was not doing any task, it was staying idle. So it will keep here until the next interrupt occurs. So there is a very critical point over here in this example which is to be noted, that in this code every time it comes back here again, it sees that if we don't unpress switch, it again sees that switch is pressed, so it sees that it is actually another interrupt, so it treats it another interrupt, so it again goes back to this, and here at it again toggles. So if we don't unpress the button with this code, it will continuously will be doing toggling. But in fact we were interested to toggle once, let for example, then it was not the proper code. However, this is proper code if we are to toggle this output bit uh, until uh, this switch is pressed. So in next any code, we will modify this code just with a little bit modification so that the controller will be treating only one interrupt whenever it is pressed. So doesn't matter how long it is pressed, it will be treated only one interrupt. So the solution lies here that to uh, enable only or to consider only one number of interrupt, we set it as edge trigger. So there are two types of uh, interrupts: level triggering, like at this level it will be considered as interrupt if we set these two bits according to these configuration 00, and these are bits this one, and if we change these two bits according to these, then it is edge triggered, and now the change of interrupt occurs according to these edges. So, and if we take these two bits, this one accordingly, this falling edge is enabled, and here on rising edge is enabled. And for this case, it was only both edges enabled. Here it was level enabled, level triggered interrupt. So these bits are responsible for level or edge triggering activation of the interrupt 1. These were for interrupt 0, and now these are for interrupt 1. So same purpose for interrupt 1 like it was for interrupt 0. So this is actually a register MCUCR. So we are to configure this register in our coding to achieve this one. So the problem which was in previous code was that until it was level triggered, so it was generating interrupt again and again, but we were interested only once. So we will use let the falling edge triggered case in this, and to do so we will have to use MCUCR register, which we'll discuss in next case. Uh, Here we skip this one, and yes, we go towards this slide which is related to our task. So if we look over here the task is resolved in such a way that no port C will be toggling only once. The change is here. At here we have made MCUCR register as falling edge triggered according to that configuration, and now only interrupt will be considered once. So there will no any multiple interrupts until it is keep pressed. So this is the change in code actually of example 5. So another code we want quickly to discuss is the C language interrupt programming. So this is the same code as example 12 of which was according to the edge triggering, but no, it will be done in C language. So the only difference is that we are now doing it in C language. So here it is being set as falling edge triggering enabling, and all other things are being done, but now it is quite easier to do in assembly language. Here it is ISR, in which we are toggling through this instruction. So all the same objective is being achieved, but now it is in C language. So that is all related to interrupt programming related to external interrupts. So we have discussed the content related to the book mentioned in the reference. Take care.